Oh, you do it again.
We'll do it again. I don't have another can. I'll bring another can
Okay,
in.
so you have a list so far. We have one bucket for the shower and this again.
All right. We'll do some explosions.
We'll do some explosions.
You know. All right. All right. We'll use that afterwards.
What's the What explodes in
There
water?
was no explosion.
No, it was
Does sodium explode in water, or what's the thing that explodes in
It's not going to be that big of an explosion. Hydrogen.
hydrogen?
Hydrogen and oxygen.
Let's do that. Let's do that one.
Yeah, we're going to do that one. Just remind me.
How about some implosion?
Well, that's what we just did. All right, so probably the biggest application of the ideal gas law is just to solve for a single variable. Equations like this, where, okay, we're given grams instead, they come up with a new equation here, it's not worth knowing. But there are some equations that are variations to the ideal gas law that are worth knowing. There are two of them that you should know. The first one is for density. So let's take a look. Gas density. And so this is an equation that you might want to be able to derive or just memorize. And it's only for gases. So gas density, well, density of anything is the mass in grams over the volume. Now, typically the volume's in milliliters, so it's grams per milliliter, like the density of water. What's the density of water?
1.
Yeah, about 1 gram per milliliter. But for gases, do you know what the typical density of a gas is? It's like 0.001 grams per milliliter. 0.001 grams per milliliter is kind of a hassle, so we change the units to grams per liter. So if we have 1,000 milliliters, then it'll be around 1 gram per liter. And so for gases, the typical units are grams per liter. Now, we would have to do it. There are two ways to get the density. One is just to weigh the gas and measure its volume. That's experimental. The other way of getting the density is by a calculation. And so how can we do the gas density by a calculation? The way we can do it is if we can relate things. Like, so we'll leave the mass alone, but volume. We know that there are other ways to get the volume. So one way of getting the volume from the ideal gas law is the volume is equal to nRT over P. And so we'll just divide both sides by P to get that. And then we're going to substitute that back in here. And so we'll end up with the mass divided by nRT over P. And then we're going to invert and multiply. So it's going to be the mass times pressure divided by nRT. And so here, if we use this equation, then we'd have to measure the mass, the pressure, the moles, and the temperature, which seems more work than this. And so it seems like we're making it more difficult, but if you recognize something in here, that is the mass should be in grams, and N is what again? N is moles. So this is grams per mole. What has the units of grams per mole? The molar mass. And so this is just going to equal the molar mass, which I'm going to abbreviate mm, times P over RT. And so what this allows me to do is it allows me to calculate the density as long as I know the molar mass. So for example, helium. The molar mass of helium is 4.00 grams per mole. So I plug that in here. Then I can calculate the density of helium at any pressure and temperature. So if I want the density of helium, let's say at 2 atmospheres and 300 degrees C, I just plug it in here. If I want the density of helium at 0.5 atmospheres and minus 10 degrees C, I can plug it in there. And so that allows me to calculate the density of helium. So what is the density of helium at 22 degrees C at 744 torr? So we know the molar mass of helium, it's 4.00 grams per mole. We have the temperature and the pressure, so we don't have to do any kind of experiment. We can just go ahead and calculate it. And so can you calculate the density of helium? Well, yeah, we can do that. Let's go ahead and do that here. So the molar mass of helium is equal to 4.00 grams per mole off the periodic table. The temperature is 22 degrees C, which is 295 Kelvin. And the pressure is 744 torr. But torr is not the unit we want. We want it in atmosphere, so I'm going to convert this. 1 atmosphere is equivalent to 760 torr. And that's going to give me how many atmospheres I have. Okay, then I'll just plug this into the equation. Let me get the pressure first. 744 divided by 760. 0.9789. All right, we can always tell if the equation's correct because the units are either going to work or not. And so it's the molar mass. The molar mass is 4.00 grams per mole. Pressure is going to be 0.9789 atmospheres. The R is 0.08206 liters times atmosphere per mole Kelvin. And then the temperature is 295 Kelvin. So let's make sure the units work out. If the units don't work out, then I must have gotten the formula wrong. And so let's see what cancels here. Atmospheres cancel, moles cancel, Kelvin cancels. So this gives me grams per liter. So the units are correct. That was 4 divided by. Helium is one of the least dense gases.
What's less than?
0.1617 grams per liter. 0.162 grams per liter. Air would be a heck of a lot more dense. You know, air would be closer to 1 gram per liter.
What's less than?
Less dense is. What's less dense than helium? Hydrogen's less dense than helium. Yeah. Hydrogen's about half the density. Okay, so let's see what they got here. Yeah, 0.162 grams per liter.
Wait, what does the MM stand for again?
Molar mass.
Molar mass.
This is mass over N. Mass over N is equal to the molar mass. So this is a useful equation to know because we can calculate the density of any gas as long as we know the molar mass of that gas. The other useful equation to know is the molar volume of a gas. So let's talk about that next. Molar volume. Molar volume is MV. And the molar volume is, how many liters of gas per mole. So if I have 1 mole of any gas, how many liters would that occupy? It doesn't matter what the gas is. It could be CO2, H2O, O2, H2. They're going to be the same. It's weird, but they're going to be the same.
That was Avogadro?
Yeah, that was like Avogadro. But that's the situation with nitrogen gas. So we just need to measure the volume for every mole of gas. Well, that requires experimental work. We can avoid experimental work by doing the exact same thing that we did for density. That is, we're going to use N now. N is equal to PV over RT. And then we're going to substitute that in this equation here. And so we'll get the molar volume is equal to the volume of the moles, and then this is going to be volume over PV over RT. And then we're going to invert and multiply. So this is going to be V. Actually, the V's are going to cancel. V's cancel. And invert and multiply. This comes out to RT over P. And so the molar volume only depends on the temperature and the pressure. It doesn't depend on what the gas is. One of the molar volumes that I had to memorize is this one. I had to memorize this. Actually, I memorized it. It was a little bit different. All right, we'll do that.
Do it now.
Well, yeah. We don't have
So they can show you the experiment.
So,
Yeah, we don't.
Like you're gonna
yeah,
do it.
just to make sure, you know, it's.
I'll get this one.
All right, you want to do this one too?
Yeah.
Okay.
But Chico gotta do it.
Yeah, I have to do it.
All right, you can do it if you want. You want to do it?
I'll do it. I'll do it.
All right.
I would want to do it.
I'll do it. How do I do it?
I'll let you go.
So I have a volunteer. I have to fill this out with.
Unrecorded, just so you're aware.
What are the dangers?
Totally safe.
Put your face really close to it. No fear. No fear.
All right. There are no flames. Danger is don't knock this beaker out on the floor.
Yeah.
I'll do it from this side.
Don't put your hand on the flame.
All right. So this is what you're going to do. You're going to
Explain the procedure. Explain the procedure.
you're going to hold this like this at the bottom.
At the bottom.
Yeah.
Roll tight.
Not real tight, but. And then just hold it at the hot.
In the
what's-
middle. In the middle.
Well, no, at the bottom. There's okay. That's enough because it's a tall can.
It's a tall can. What am I doing?
And then just heat it to the hottest part of the flame. What's the hottest part of the flame?
It goes like,
Right here.
Yeah.
I just hold it there for a couple seconds.
Wait, what's inside
Well,
this
you
can?
want to stand here on this side?
Oh yeah. It's just water?
Yeah, it's just water.
So what's gonna happen?
You'll see.
You'll see.
You want this? You want this recorded?
Yeah, I don't mind.
All right. We'll record this.
You're gonna be famous, kid. You're gonna be on YouTube.
Wait. Now I'm scared. Now because everyone knows something.
You're gonna be a star.
Just let it boil.
Just let it boil.
Yeah.
How long does that take? Like 20 seconds?
It's gonna take about 10 minutes.
10 minutes?
Hopefully, it won't take so long.
How do I know whenever steam starts coming up?
Yeah, when steam starts coming up and it's boiling at a vigorous boil, then what you're going to do is you're going to remove it from the flame, flip it upside down, and put it in the water. So you want to do that quickly. So flip it upside down, put it in the water. Once it starts to boil. So just,
Oh, I can hear something.
yeah, you can hear it boiling, can you?
Oh, there's
Yeah,
the
and
steam.
then
Is it
yeah,
time?
just
Oh
no.
yeah.
Try to get a lot of steam coming out.
A lot of steam. Get your face right in
Okay,
there.
don't lower it too
Oh,
low.
don't lower it.
Yeah, just get it on the hottest part of the flame
Gotta
there.
get real close, alright?
Yeah, and when you see, does that look like? Yeah, that's looking pretty good. Then what you're gonna do is you're gonna invert it and put it into the
Now.
beaker.
Okay, so
yeah,
you
you could do it now.
flip it
Quick
inside the
Oh
wall.
wait, that's too
That's too slow?
slow. Too slow. You gotta do it. You gotta do it
Quick with
faster.
it, you know, the flash.
Alright, hold up.
Yeah, try to do it.
Because what if you make me miss? I'm gonna miss and feel
You
dumb.
don't want to kid.
Because this is my left hand. Like, what the hell?
Oh, are you right-handed?
No.
You can switch it.
I'm ambidextrous. It's just,
Alright.
this one doesn't feel comfortable.
All right, go ahead.
Be steady, alright?
There's a target is right there.
The can's broken. The can's broken.
Here.
Do it again?
You can do it again. Here, I need to get a little bit more water. Okay.
You want to do it? No, I'll let Shabal do it.
Here. Okay. Hold it like
Over
from
here.
underneath. Yeah, from underneath from there.
Underneath.
Yeah, like that. You got
Yeah,
it?
yeah, that's better.
Okay,
That's
then
You
it's
want the
easier.
top of it to go in the water.
Yeah, and then what you want to do is you want to do it quickly so that this.
Wait, practice.
You got it. What you have to do is you have to submerge the top here
Into
quickly.
it.
Yeah.
Oh, like it get in.
Yeah, you wanna seal the hole there.
I thought I was
with the
trying
water.
to like.
No,
drop
you
the
don't want to
water
pour.
in.
You don't want to pour it in
No pouring.
there.
No pouring. Okay.
No, no pouring. You know how we put the water?
I didn't know. I thought I was supposed to pour it in. Come on, now you didn't explain that properly.
Oh, it's ready.
Is it ready?
So you gotta be quick with it. I see it as you speak.
Yeah. So just mentally, like visualize what you're gonna do and then do it. But you want to face. You're blocking the view there.
Feel like an extension of your
Yeah.
body.
Just visualize what you're gonna do first and then do it.
Gotta prepare.
You got it. You got to do it in one motion. Flip it upside down and then submerge it.
All right, here I
Submerge
go.
the top.
Ready?
Yeah.
Ready? All right, here I go.
That was a great reaction. Thank you.
That was more like, I thought it was like a bunch of steam was gonna come out or something.
Oh, that's pretty good.
I'm thinking that the NC or I do have a couple videos
Many of the
of
views
either
like
doing
tomorrow.
experiments and then being like surprised by the results.
Okay.
We make a compilation and
Oh.
then show it on the last day.
Oh, that's a good
It should
idea.
include some of those bloopers when you miss.
Nah, that was lack of explaining. You guys didn't explain it for me.
Well, yours came out better than mine.
Yeah, come on now.
So that's
Come on
good
now.
technique there. Yeah.
I missed it. Right? So happened. I got
Oh, that was fun.
I was expecting steam. I'm not gonna lie, I was expecting like.
So I got a phone call right away. I was like, no, not right now.
All right.
Braxton's about to flip
So we're doing the molar volume, and I had to memorize this molar volume here when I was taking Chem 4. Actually, I think I had to memorize it in high school. And that is the molar volume of the gas at STP. Have you heard of STP? Standard temperature and pressure.
Did you take AP Chem?
No.
He was teaching AP Chem in high school.
He was
No.
the AP.
No, everybody said stay away from chemistry. You know, that's the worst class.
Yeah, you didn't do
And
very
so,
well.
but then I took chemistry and it wasn't so bad. Then I thought,
What'd you get?
wow.
What'd you get in Chem 4? In your version of Chem 4? You got a C.
I know. Could be. Could be. You know, I wasn't a chemistry major at the time, so. But I think I got a B in Chem 4. I didn't take it very seriously.
I would love a B.
Oh,
And then, no, I want. Of course, after that, I want to get A's in chemistry. But actually, honestly, I don't remember. Chem 4, the grade doesn't count for transfer. You know.
You remember
For
your
Chem
first
4,
day
yeah.
class, you know, what was that whole story about UCLA? You don't remember you remember everything about UCLA? You don't remember Chem 4?
Do I remember everything in Chem 4?
You remember your roots. You remember
Oh, yeah.
This doesn't count.
I remember a lot of it. One thing I remember is the molar volume of a gas at STP. I haven't been able to forget it. It's one of those things that,
Is that this one?
yeah, it's this one, except I remember the one for 1 atmosphere. And we were required to memorize it. And so I memorized it, and I worked hard at memorizing it because it wasn't so easy to memorize. And do you know how many times I've used it since Chem 4? Zero. And I cannot unforget it. You know, I want to, so I can clear up some more memory, so I can memorize more important stuff, but I can't, you know.
What would be the first thing you do that memorize with that like free space?
Well, with that free space, I'd rather memorize, standard temperature is 0 degrees C for gases. And standard pressure is 1 atmosphere or 1 bar. And we can measure the molar volume at here. It comes out to, with 1 bar, it comes out to 22.7 liters per mole. In 1 atmosphere, it's 22. Well, anyway, what I remember instead of this is this. And this is what you should know. Because the problem with standard temperature is who works at 0 degrees C? A lot of people?
Not a lot.
Not a lot?
What's the question?
How many scientists work in a 0 degrees Celsius laboratory?
Would someone? Oh yeah, Antarctica.
Well, if the fume hood's at 0 degrees C, you need the lab to be at 0 degrees C, or you would need other things to be at 0 degrees C to maintain that pressure, because the fume hood's sucking in lab air. And so, actually nobody, I know nobody who worked at 0 degrees C, and I never worked at 0 degrees C.
23 degrees.
And so, what we do instead here is, rather than memorizing the molar volume of the gas at STP, it's probably better to memorize the molar volume of a gas at room temperature in standard pressure. And so this is a useful number to memorize. MV at RT, room temperature, and 1 atmosphere or 1 bar. RT, well, what is room temperature? Room temperature is going to be 25 degrees C or 298 Kelvin. And so that's much easier because you can set the thermostat in the lab for 25 degrees C and you can work in a 25 degrees C lab versus setting the thermostat. If you set the thermostat at 0 degrees C, then you got to worry about things freezing. You know, all your water solutions are going to freeze, et cetera, et cetera. And so here, this is much more useful. So the molar volume of the gas is equal to RT over P. And so R is 0.08206
Professor,
liters.
this is an important question. Why doesn't alcohol freeze? People always put their bottles of like liquor in the freezer.
They don't freeze. They don't freeze.
And they don't freeze?
Because it's liquor.
Why not? You're the expert. You told you to synthesize your
Is
own
it like a certain
alcohol.
temperature?
Probably the liquor.
Afterwards it freezes?
It's probably like the molecule
You know,
bomb
temperature.
that's causing your mouth.
It depends on how much alcohol there is in there.
More like a bar.
The more
What about
alcohol.
like 35% alcohol?
Yeah. A lot of things don't freeze. It's like when you're making ice cream, you make salt water, and the salt water doesn't freeze, it stays a liquid.
Alcohol just doesn't freeze.
It doesn't freeze, it will eventually freeze, but it doesn't freeze because of colligative properties, and we're going to be talking about colligative properties, actually. This is why they salt roads and they do other stuff. But we're going to be talking about it in the next chapter or two.
I go straight by here. And I check my
We'll go into 98.15.
How about you? You over?
What is it? That's the number you want to look up?
Yeah. Well, we're going to make it a little easier.
So is that what you're saying? Oh, you have it memorized.
Yeah, this is a number that if I memorized it, it would have been much more useful.
What number?
Okay, what we're going to do is we're going to make it even easier to memorize. This is to 4 sig figs.
Yeah, five.
Well, if I don't count the 6. Actually, let's do it to 4 sig figs. To 4 sig figs, it's going to be 24.47
Yeah.
liters per mole. So 1 mole of any gas is going to occupy 24.47 liters, or to 3 sig figs, it's just going to be 24.5 liters per mole. And so this is much more useful. Room temperature and normal pressure, a liter, actually 24.5 liters of gas is equivalent to 1 mole of gas.
So how many significant figures should we memorize?
3 sig figs. So you should memorize this to 3 sig figs. A lot of people will have you memorize this, 3 sig figs, but this is not so useful because 0 degrees C.
So you remember 24.5?
So I remember 24.5. I have that number memorized. 24.5 or about 25 liters. Okay, but that's in atmospheres. What is the molar volume of a gas at RT and 1 bar. And so we need to know what's the difference between an atmosphere and a bar. Well, 1 atmosphere is equivalent to 1.01325 bar. And so an atmosphere and a bar are almost the same. You know, it's about 1% difference. And so if we're at 1 bar pressure, that's almost one atmosphere of pressure. Now, what's bigger, an atmosphere or a bar?
Bar. Is that?
No, what's bigger, an atmosphere or a bar?
Bar.
An atmosphere?
An atmosphere is bigger.
Do they have the
Yeah.
same pressure?
What's bigger? An atmosphere is bigger than a bar because it takes more than 1 bar to fill up an
It's like
atmosphere.
$1, $2,
That makes sense.
But I thought 1 ATM equals 1.01
Think
bar.
backwards.
Think of it like money.
Yes.
$1
Yeah.
US dollar equals 1 Japanese
Oh,
dollar.
dang, I get it.
All right.
1 atmosphere dollar equals 1.01325 bar dollar.
So can you calculate the molar volume at, this would be more useful to know. The most useful is going to be this one here. But this one is okay too. Can you calculate the molar volume at room temperature and 1 bar?
We're calculating it as temperature?
Yeah, room temperature and 1 bar. 298.15 Kelvin.
Oh, that one we're doing for volume.
Yeah.
Okay.
This one's in atmospheres, this one's in bar.
I had a calculator.
Is it the same temperature?
Same temperature.
$24.79.
24.79.
And then 46 would be 24.8.
Yeah. All right, did other people get this 24.8?
Not sure if that's right.
Yeah, that's right. And so let me just say in the final minutes here. Okay, so at room temperature and 1 atmosphere, we have 24.5 liters per mole. And then if we go room temperature 1 bar, a bar is less pressure. If we have less pressure, what happens to the gas? Does it expand or contract with less pressure? It expands. And so, they're almost the same. You know, bar and an atmosphere are almost the same. And a bar is just a little bit less. And so the gas expands to 24.8.
It's less.
A bar is a little bit less pressure than an atmosphere. And then this is at room temperature. But what if we cool it down to 0 degrees C? Does the gas expand or contract? It contracts. And so if we go from room temperature, it will be 24.8. And then we go down to 0, it goes to 22.7. So it contracted significantly. And so these are all molar volumes under different conditions. And so the molar volume is going to depend on the temperature and the pressure. Since that's the case, let's pick the most useful temperature, room temperature, and the most useful pressure for us would be 1 atmosphere of normal normal pressure. And so this is the number you should memorize, not the other number. So
That's the standard gas.
yeah.
Standard gas.
Yeah, and this is for any gas, and it doesn't even have to be a pure gas. So for example, we could take a mixture. So an air is a mixture of nitrogen and oxygen plus some other gases. So we could calculate the molar volume of air. And so a mole of air would just contain 6.022 times 10 to the 23rd molecules of gas. And it would just be a mixture of gases. So if we did air here, do the molar volume at 11 degrees C and 1.33 atmospheres, the molar volume comes out to 17.5 liters. So it's quite a bit smaller. It's because of the lower temperature. I mean, and the higher pressure. Actually, it's quite a bit smaller. It must be because of the higher pressure, 1.33 atmospheres. And, well, it's a combination. I don't think we have enough time to start stoichiometry, so I'm a little bit behind. So I'm going to wait for stoichiometry. We'll just end now.